Welcome back, everyone. I'm Jordan Giesegy, and this is The Limiting Factor. In the last video of the Gigacasting series, we covered crashworthiness, and now it's time to look at the economics of gigacastings versus their competition, advanced high-strength steel. For the past decade, there's been a trend away from conventional steel and towards advanced high-strength steel and aluminum to lightweight vehicles. So far, advanced high-strength steel's been winning out over aluminum due to its lower cost. However, Tesla's front and rear underbody castings for the Model Y may blow the entire steel versus aluminum cost model out of the water and replace it with a new benchmark. Before we begin, a special thanks to my Patreon supporters and YouTube members. This is the support that gives me the freedom to avoid chasing the algorithm and sponsors, and I hope will eventually allow me to do this full time. As always, the links for support are in the description. Around 10 to 15 years ago, regulations and customer preference began forcing vehicle manufacturers to use increasing amounts of advanced high-strength steel and aluminum. These lighter weight, stronger materials improve energy efficiency, which in turn lowers carbon emissions, increases vehicle range, and reduces the lifetime costs of owning the vehicle. Most people understand that aluminum can reduce the weight of a manufactured product. Advanced high-strength steels, on the other hand, aren't well known by those without a manufacturing background. We'll call advanced high-strength steel just high-strength steel for the rest of the video. Conventional steel and other metals are actually crystalline materials. High-strength steels are newer alloys of steel with complex crystal structures that offer double or triple the strength for the same weight as conventional steel. Furthermore, progress is being made year by year to make even better steels. Currently, Generation 3 of advanced high-strength steels is starting to roll onto the market, making it increasingly difficult for aluminum to compete with high-strength steel for lightweighting vehicle bodies. With that background in mind, let's start comparing aluminum to high-strength steel. Why would Tesla choose aluminum over steel? The obvious answer might be that aluminum alloys have a higher strength-to-weight ratio than conventional steel alloys. But is that true for Tesla's new cast aluminum alloy compared to high-strength steel? In short, no. The high-strength steel alloys used in vehicles have a strength-to-weight ratio of 121 to 1. Tesla's cast aluminum alloy has a strength-to-weight ratio of around 50 to 1. The higher the ratio, the better. So the strength-to-weight ratio of high-strength steel is more than double that of Tesla cast aluminum. What about material cost? Again, steel has aluminum beat. Prices for metals are currently inflated, so we'll use a rough average of past metal prices. Let's assume a high-strength steel price of $1,500 per ton and an aluminum price of $2,000 per ton and factor in the strength-to-weight ratios. This leaves us with $12.40 per unit of strength for steel versus $37.74 per unit of strength for aluminum. This means that Tesla cast aluminum is roughly 3 times more expensive per unit of strength than high-strength steel. Surely then, an aluminum vehicle body would therefore be too costly to consider, even with Tesla's alloy and gigacasting. Let's dig deeper. According to a study by MIT led by Joshua Bird, an aluminum body for an electric vehicle, excluding paint, costs about $2,200, whereas a high-strength steel body costs $1,100. That is, an aluminum body costs $1,100 more, which doubles the cost. Earlier, we saw that at the material level, aluminum costs 3 times as much. So, as we move along the production chain, aluminum is starting to close the cost gap with high-strength steel. Note that this analysis was for a full vehicle body rather than just the underbody. The cost analysis also assumed that an aluminum body would use mainly stamped rather than cast aluminum. Although aluminum is starting to look better here, it still costs around $1,100 more. I'm not including paint here because apart from some overspray, the gigacasting isn't painted. I'm attempting to target just the cost of the body structure. When we move up to the vehicle level, an aluminum body only costs about $500 more than a high-strength steel body. In other words, if we factor in all costs at the vehicle level, a steel body costs $1,100 and an aluminum body costs $1,600. What's going on here? how does high-strength steel lose most of its strength, weight, and cost lead to aluminum at the vehicle level? Vehicle parts generally need to be stiff. The stiffness of a part is determined by the material a part is made from and the geometry of the finished part. The Young's modulus of steel, which measures stiffness, is roughly 29 million psi, whereas for aluminum, it's 10 million psi. So, at the material level, steel is clearly stiffer, but there's a twist. The density of aluminum is 1/3 the density of steel, meaning a part made from aluminum will be nearly 3 times thicker than a steel part of the same weight. Stiffness increases by the cube of any increase in thickness. That is, thickness has a powerful impact on rigidity. If we take into account both Young's modulus and density, an aluminum part can be half the weight of a steel part and still achieve the same stiffness. Total fatigue and strength characteristics also play a role here, which requires more material and weight. But overall, the key point is that aluminum makes up for its handicaps through greater rigidity for the same weight, despite being 1/3 the strength of steel. The net result is that when aluminum is used for a vehicle body instead of high-strength steel, the body ends up weighing 23% or 58 kilograms less. At the vehicle level, the weight savings increases to 93 kilograms. That is, a 58 kilogram decrease in weight from the aluminum body results in an additional 35 kilograms of weight savings in other parts of the vehicle versus high-strength steel. The other parts of the vehicle that we're referring to here are the battery, motor, and chassis. The battery and motor, or powertrain, is one of the most expensive systems in an electric vehicle. Even a kilogram of weight cut in the powertrain is worth about $30 to $50. In other words, aluminum is expensive, but the lighter weight of the aluminum vehicle body allows the use of a lighter powertrain, which pound for pound is one of the most expensive parts of the vehicle. The obvious question here is, with battery costs continuing to fall, won't the cost of a steel body look more appealing over time because the powertrain will cost less? Yes, and by 2030, steel's cost advantage should continue to grow from around $500 to around $650 versus an aluminum body. That is, unless you're Tesla. It looks to me like Tesla will be able to use more aluminum in their vehicle bodies for cheaper than what's indicated in the MIT paper. Although the latest version of this research paper was published in February of 2021, there's no mention of Tesla's gigacastings, which I think will invalidate the cost model. As we saw earlier, a steel body ends up costing $500 less than an aluminum body. For an aluminum body, roughly $900 of the cost is manufacturing and assembly. Gigacastings do require manufacturing and assembly, but it mostly occurs in one 3-minute step rather than involving hundreds of robots and hours of time on the assembly line. If that's the case, is it possible that the cost of an aluminum body could be reduced to near the cost of a high-strength steel body? And taken a step further, if a Gigacast aluminum body uses less aluminum than a stamped body, could we see cost parity or a reduction in cost by moving from high-strength steel to a Gigacast aluminum body? I haven't been able to locate the answers to this with publicly available information, but that isn't a surprise given how new Gigacasting technology is. However, I have come across information that might act as a bridge to the answer. According to the Freedom Car Fuel Partnership run by the U.S. Department of Energy, or DOE, magnesium castings that don't require a heat treatment or coatings cost 10% less and weigh 60% less than conventional steel stampings at the structural component level. By structural component, it appears they mean a collection of parts. Let's take the comparison of magnesium versus conventional steel and use some basic logic to arrive at a comparison of aluminum versus high-strength steel. In other words, we'll use informed speculation to arrive at estimates for the cost and weight savings of gigacastings versus high-strength steel. Let's start with weight. Indications are that magnesium castings weigh about 33% less than aluminum castings, placing the weight reduction closer to 40% rather than 60% for cast aluminum versus conventional steel. But 40% is of course high because we need to compare against high-strength steel rather than conventional steel. As discussed earlier, stamped aluminum offers a 23% weight reduction over high-strength steel. If we set the MIT estimate of 23% as a minimum and the adjusted DOE estimate of 40% as the high end, that leaves a weight savings of between 23% and 40% by using gigacastings instead of high-strength steel. Now it's time to move on to cost. The DOE indicated a 10% cost reduction at the component level for a magnesium part versus a conventional steel part. How does that translate when comparing cast aluminum parts to high-strength steel parts? Although advanced high-strength steel is 2 to 3 times stronger than conventional steel, it costs 3 times more. So, in terms of cost savings at the component level, it provides minimal, if any, cost savings. That means at least in terms of cost at the component level, we can compare a cast magnesium part directly to a high-strength steel part, which means a 10% cost reduction of cast magnesium versus a high-strength steel part. All that's left to do now is to swap out the magnesium for aluminum. I'm going to say that this comes out in the wash and stays at 10% for 3 reasons. First, although magnesium tends to cost more than aluminum, the price difference can sometimes invert, with magnesium being cheaper. Second, the magnesium part will weigh 30% less, meaning less material used and less cost. Third, there isn't a cost model available for magnesium versus aluminum gigacasting. In all likelihood, the aluminum parts would be cheaper, but I'm looking to build a conservative estimate here. A 10% cost reduction for aluminum versus high-strength steel seems paltry, but even break-even would be a massive victory. Why? The MIT paper stated that an aluminum body would cost twice as much as a high-strength steel body. That is, break-even would mean an $1,100 cost savings. If we add in an additional 10% for Gigacast instead of stamped aluminum, it results in a $1,200 cost savings. But let's dial that in a bit more. Tesla won't be using a full aluminum body, just the front and rear underbody. So how much of the $1,200 cost savings will Tesla be able to take advantage of? Replacing the front and rear underbody allows for at least 2/3 of the robots in the body shop to be removed, and that number could actually be on the low side. The underbody is the thickest, most complex, and strongest part of the vehicle body because it's load-bearing, meaning expensive. 2/3 of $1,200 is $800, and after subtracting the $800 savings from the original cost of $2,200, Tesla is getting a 66% aluminum body for $1,400. That is, a cast aluminum body is only $300 more than a high-strength steel body. This is much better than the $1,100 cost premium we saw for stamped aluminum. From there, we still need to take into account vehicle-level cost savings. Earlier, I showed that Tesla could save $600 from an aluminum body due to a lighter powertrain. 2/3 of $600 is $400. The $800 cost savings from the cast aluminum body plus the $400 cost savings from the powertrain savings is $1,200. Subtract $1,200 from the original starting price of $2,200 for stamped aluminum, and the vehicle-level cost for a cast aluminum body is $1,000. This is $100 less than the high-strength steel body. Note, this is conservative. If I add all the trimmings back in, we're probably looking at closer to $220, or 20% less than a high-strength steel body. That is, overall, the informed speculation I've run you through here leaves us with $100 cost savings on a vehicle with a production cost of $20,000. That's a 0.5% manufacturing cost reduction. If that's right, at a million vehicle run rate, Tesla will save more than $100 million a year with gigacastings. The game of cost and weight savings in vehicle manufacturing is usually measured in grams and cents. Tesla's going after 50 to 100 kilograms and hundreds of dollars. More importantly, Tesla vehicles will have greater efficiency, which gives Tesla the option to make vehicles with longer ranges or make more vehicles with the same number of battery cells. And for the kicker, we haven't yet factored in that Gigacastings will accelerate the speed and precision of the manufacturing line, which has multiple knock-on impacts for cost. I have no way to calculate this, but if you know of a way, let me know in the comments below. One point we've been dancing around here is that Tesla is doing gigacastings for the front and rear underbody. But what about beyond the front and rear underbody? Tesla's definitely been toying with the idea. This drawing is from a 2018 Tesla patent application that shows a way to cast the rest of the vehicle body. With that said, my assumption is that Tesla will continue to use steel for other parts of the vehicle. To understand why, let's first look at why other automakers haven't adopted gigacasting. In the original gigacasting video, I provided a high-level answer. It boils down to internal politics and company culture. Overall, I'll stand by that as the ultimate reason, but I'll add some nuance here. Automakers are slowly increasing the amount of lightweight material they're using in vehicles, but the uptake of high-strength steel is expected to be far more rapid, increasing from 7% to 13% of vehicle weight between 2015 and 2022. In the same time frame, aluminum sheet will increase from 1 to 2% of vehicle weight, while forged, cast, and other aluminum will remain steady. There's clearly an interest in reducing weight, but more through steel than aluminum. Why? First, as we've just seen with conventional stamping techniques, aluminum was assumed to be more expensive. Second, most automakers aren't growing, and their factories are set up for stamped and welded steel bodies. If they switch to gigacasting, they'd have to tear out equipment and spend the money on new equipment. Tesla is at less than 1/20th of its target vehicle production of 20 million vehicles a year. This changes Tesla's frame of mind. Their main concern is figuring out how to grow 20x in 10 years, as quickly and with as little capital as possible. Third, the engineers at legacy auto manufacturers have developed a lot of skill in-house for stamping and welding sheet metal. It may be far simpler just to upgrade from conventional steel to high-strength steel. From their perspective, steel just keeps getting better and cheaper as new steel alloys are developed. Cast aluminum uses a different skill set entirely. Fourth, there was a concern in the automotive industry that if everyone moved to aluminum, that the price for aluminum would skyrocket. If it is true that using large amounts of aluminum in vehicles would cause a price spike in aluminum, it looks like Tesla might run away with the cheap aluminum contracts. If other competitors decide to start using aluminum as well, Tesla will have already secured their aluminum at low, pre-demand spike prices with long-term contracts. This is also why I said earlier that I don't think Tesla will go all in on aluminum. By using aluminum strategically and high-strength steel in other areas, Tesla diversifies the materials used in their vehicles, which will help insulate them from price spikes. It's worth noting that some manufacturers are starting to use more and larger aluminum castings. I expect Chinese manufacturers in particular to be right behind Tesla. Among Western OEMs, Ford appears to be investing heavily in larger castings. But there are large castings, there are gigacastings, and there are Tesla gigacastings. The difference isn't just the size, but also the ability to produce a casting that doesn't require heat treatments, coatings, and doesn't require machining. How has Tesla managed to create castings that eliminate several of the key manufacturing steps usually required for castings? That's what we'll look at in the next 2 videos in the Gigacasting series. In summary, in the past 10 to 15 years, there's been a competition between aluminum and high-strength steel in automotive vehicle bodies, even before the advent of all-electric vehicles. With all-electric vehicles, a lightweight vehicle body is even more important because any weight that can be saved allows automakers to remove batteries from the vehicle, which have a high cost per unit weight compared to structural materials. All indications were that the market was moving to high-strength steel because when it's used in vehicle bodies, it results in a cheaper product at the vehicle level. The study from MIT indicated that an aluminum body would have a cost structure double that of a high-strength steel body, $2,200 versus $1,100, and would cost $500 more at the vehicle level. However, Tesla's approach with gigacasting could flip the cost model on its head, reducing the cost of a vehicle body that's 2/3 aluminum below the cost of a high-strength steel body by up to $100. This speculative but fairly solid estimate of $100 was purposely conservative. It was conservative partly to steelman the case for gigacastings, and partly because there's no accounting available for the positive impacts of gigacastings further down the production line. Those include fewer quality checks, more uptime, less rework, and faster production ramps. In the next Gigacasting video, we'll take a look at Tesla's Gigacasting alloy patent to find out how and why Tesla's alloy is unique. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video. I'm also active on Twitter. You can find the details in the description, and I look forward to hearing from you. A special thanks to Jeremy Hamawi, Thomas Maxwell, and TJ for your generous support of the channel, my YouTube members, and all the other patrons listed in the credits. I appreciate all your support, and thanks for tuning in.